This video presents some background information on biochemical oxygen demand, which is a measure of organic materials in water. As you might remember, organic materials contain carbon, with the exception of carbonates and CO2, which are considered inorganic. Organic compounds are susceptible to biological decay. Things that are highly biodegradable include starches and proteins and food and sewage. Organic compounds that aren't easily biodegradable are plastics. And biodegradation rates vary depending upon temperature and the kind of organic material. So why should engineers care about this? In the environment, microbes consume organics and in the process also consume oxygen. And that oxygen consumption can be great enough to reduce the DO levels in the water enough to kill the fish. In the air, at 21% oxygen, there's over 200,000 parts per million. In water, saturation concentrations, depending upon the temperature, are more in the vicinity of 10 parts per million. And so fish don't have a real big buffer there. So let's talk about BOD reactions in a bottle or a batch reactor. Organic material is in the water. It's going to be consumed by microorganisms and converted to CO2 and water and minerals and other organics, mainly other microorganisms. And as you learned in class, we'll often model this process as a first-order decay process. So if we start off with a concentration of organic material of L sub naught, over time, that concentration will decline as the bacteria do their work. Now in BOD, we recognize the fact that as the bacteria are consuming this organic material, they are also consuming oxygen. And so this process is said to exert an oxygen demand on the local environment. If there's biodegradable organic materials there, oxygen will be demanded of the local environment by the bacteria to degrade those materials. So in a test, we actually are going to let this happen in a bottle and measure it. We get a glass bottle, we add organic sample and bacteria. They're naturally occurring in most cases, but if you have a sterile sample, you might have to seed it with bacteria. We will probably dilute it, and then we'll measure the oxygen at time 0 and at some other time later on. To measure this, we'll define BOD as the mass of oxygen consumed per liter of sample. The mass is going to be the change in concentration times the volume of the bottle. Here's the volume of the sample. Bottles are a standard 300 milliliters. And so with a little bit of math, we can come up with an equation that says that BOD at time t is the dissolved oxygen at time 0, or initial, minus the dissolved oxygen at time t divided by the volume of the sample divided by 300, which often is given the name the dilution factor, or P. So if you see DO minus DO over P, this is the same equation. And look, as time goes on, what happens? The dissolved oxygen at time t drops and drops and drops as the bacteria consume it. And so the BODT climbs over time. So this distance here is what we're measuring in the test, and we're calling it BOD at time t. Now eventually, over a period of 20 to 30 days, all of the organic material will be consumed, and this rise in oxygen consumption will level off and stop. And it stops at a point that we're going to call the BOD ultimate, the BODU. And in this case, ultimate comes from the fact that it's the last value, or in some books they call it the limiting value. This is the upper limit, and so they'll call this BODL. BODL and BODU are two different names for the same thing. Now in practice, we don't want to wait 20 to 30 days to get this value, and so we typically measure BOD5. That's the standard time. In this class, we're going to measure a BOD7 for convenience. Now, in the bottle, as the organics are degraded, the bacteria use more and more oxygen. When all the organics are gone, the oxygen consumption stops. And so you can see that, in fact, the initial organic concentration measured as milligrams of oxygen per liter is the same as the BODU. Now this allows us to do some math. At any time t, the BODU here is the oxygen consumed, this value, plus the oxygen related to the organics that have not yet been consumed. So this is the amount that's left at this time. This is the amount that's been consumed, and the total is BODU. So this allows us to do a little bit of math. BODU is the oxygen consumed plus the oxygen demand of the remaining organics. If we label the oxygen demand of the remaining organics, if we model that as a first order decay, we can use BODU e to the minus KT. The oxygen consumed is the BODT that we measure. And you can do a little bit of math. I'm going to bring the BODT to the other side and collect terms to get this equation. This equation can be used to relate BODT, which is normally measured in the lab, to BODU if you know the reaction rate. So when you're talking about BOD, you can talk about BOD as the organic material that's in the water. Engineers will say water has a certain amount of BOD. They're talking about the concentration in the water, and that concentration declines over time as bacteria consume it. And in the lab, what we measure is the BOD that is exerted in a test. You can think of BOD as a potential oxygen demand that in the test, that demand is exerted. It happens. And that's what we're measuring in order to discover what's in the water. And the equation that describes this red curve is this equation, and the equation that describes the blue curve is this one. So students often have difficulty relating the bottle BOD to environmental BOD. I'm hoping that this little demonstration will help. Let's imagine that we have a river here, and we're going to take a sample from a spot on the river and put it into a bottle test. So this sample would produce this curve, which of course is described by this equation. Now this curve looks like it's going to flatten out here at a BODU of around 100. So this tells us that the BODU of the water taken at this spot was 100. Now what about other places on the river? Well, if it's 100 here, as the water travels downstream, bacteria are consuming the organic material, and the BOD in the water is declining. This curve, of course, is described by first order decay. Now suppose we came out and sampled the water 8 days travel time from our previous sample. Well, at this point, we should expect that the organic material that was 100 at the beginning has declined quite a bit. And in this case, it's around 20. And if I were to take this water sample and put it into a bottle test, I would get this curve. So notice that this curve is flattening out at BOD 20, or ultimate BOD 20. Now in practice, we would come in and we'd say, well, this sample, the upstream sample, had a BOD 5 of 60, 62, and it would have, the lower downstream sample would have a BOD 5 of about 7. And that 62 and that 7 are 2 points on this curve. 62 and 7 are the BOD 5 points. And of course, this curve I drew in terms of BODU. So I'm hoping that helps you see the relationship, but also the differences between a bottle test, which goes up, and an environmental BOD, which goes down.